Today we'll start with it, probably won't finish it.
Got a question.
Yeah.
Can you go back up?
Yep.
So on the graph, it's x to the fourth. Why is the and the
Okay, because of the negative. Because we're multiplying it by -1. Right, so x to the fourth goes up with the coefficient's negative, it's going to go down. Okay? All right. So next issue then is a rational function. How can we deal with a graph of a rational function? As you might expect, it's a little bit more complex, but maybe not a ton. And we're going to use the same approach, right? We just want to know where are the x-intercepts, what's the end behavior of the function, and then we got to be able to figure out what's going on in between all the x-intercepts. But there's one other little thing we have to deal with here that we didn't before. For a polynomial, what's the domain of the function? All real numbers, right? Polynomials are very well-behaved functions. There's no place where you have to ever exclude from the domain. It's always all real. So we can go from negative infinity to positive infinity. There's no values that we have to exclude. Okay? Is that the same thing here? No, we've already dealt with this a little bit, right? There's some values of x we have to exclude from the domain because we can't divide by 0. So what's clearly the first thing we want to do with this function, probably, this rational function? Factor it. Factor the top and factor the bottom. So on top, what can we factor out? -4. Leaving us with, okay, bottom factors into +2. Okay. Good. So then there are some values we have to exclude. What are the values that x cannot be? X can't equal 5 and x can't equal -2. Okay? So those are places we want to put those down right away. Those are kind of red flags. You got to know what's going on at those places. So at -2 and +5, the function does not exist. Okay? Okay, so y is undefined. Okay? Are there any places where the function is equal to 0, where it would equal 0? Because now think about this. Where does a fraction is undefined where the bottom is 0, right? But a fraction is equal to 0 where the top is 0. 5 divided by 0 doesn't make any sense, right? That's an undefined concept. But what is 0 divided by 5? 0, okay? So we'd look for the zeros of the numerator. Well, where is the top equal to 0? 5. So normally we'd think of that as being an x-intercept, but what's the problem here? It's undefined at 5, so it can't be, right? The function does not exist there, so it can't be an x-intercept, okay? All right, so we'll get to that in very shortly. Let's think about the end behavior though first. So we're going to figure out, we'll figure out like what we're going to do here to test some points and kind of maybe what all this stuff means. Before we go there though, let's look at the end behavior issue. Okay, so I've got, before we looked at only the impact of the leading term. Because as x approaches positive or negative infinity, it's the leading term of a polynomial that becomes significant, right? So for this function here, as x approaches plus or minus infinity, what's the function doing? Well, the limit of f of x as x approaches plus or minus infinity would just be the limit of the ratio of the leading terms, right? In the top polynomial, the only term that matters is going to be the -4x. In the bottom polynomial, as x explodes, the only term that matters is the x squared. And so we can just look at the ratio of those two terms. What does that simplify to? What is -4x divided by x squared? Okay, so that's going to become the limit of -4 over x. Okay, now let's think about the behavior of that. If I've got a fraction that's got a -4 on top and the bottom is an x, and x is approaching positive or negative infinity. Now what's happening to these fractions? If I start off with -4 divided by 1, that's -4. -4 divided by 10 is 0.4. How about if I make it -4 divided by 1,000,000? Well, I don't care what it is it big or small? Very small. -4 divided by a quadrillion. Really small, right?
Small.
Negative 4 divided by a number that's approaching infinity, that fraction's approaching what value? Did everybody see that? 0, because the bottom is getting infinitely big. Think about the behavior of a fraction. If the top is staying the same, but the bottom is getting infinitely big, that drives the size of the fraction to 0, right? I'll prove that to you in calculus. I'll actually go through a little proof of why it works that way. It's not a hard proof, but for now, I don't want to take the time. You just take it on faith. It makes sense conceptually, doesn't it? Right? That if the bottom is more powerful than the top, has a bigger power of x than the top, as x goes to infinity, the bottom is going to explode infinitely faster than the top, which drives the fraction to 0. Okay? So what's that mean? As x approaches plus or minus infinity, the function, meaning y, has a limit of 0. What's the behavior of the function going to be then as the ant walks to the right forever, for example? What's his y value going to settle at? 0. How about if he goes to the left forever? 0. Okay, so we say then that the function has what's called a horizontal asymptote. And we can put that in there. Okay, the horizontal asymptote. So there's our horizontal asymptote. The horizontal asymptote is the line y equals 0. What's that mean? Infinitely far to the left, or the right, infinitely far to the left, the function is going to stick to that asymptote. It's going to approach that asymptote and kind of try to stick to it, right? But it doesn't tell us what's happening in here. It tells us about the end behavior. In the last example, the end behavior was really dramatic. In the last example, the end behavior was we're plunging down to negative infinity at both sides. This one's kind of more boring this time, but it's also can be useful to us. In this case, the end behavior is that the function is just going to end up sticking to these asymptotes. Okay, we got to figure out what's going on in the middle. Okay, so let's explore this a little bit. What's going to happen as x approaches? These are the values that we can't have, right? What's going to happen as we approach a value of negative 2? Okay, let's take a limit and see what happens. Let's just explore this, and then we'll look at a graph of this and then kind of make sure we'll graph it on Desmos and we'll see if our predictions are what actually happens. So the limit of negative 4 times x minus 5 over x minus 5 times x plus 2 as x approaches negative 2. Okay, well, as x approaches negative 2, what's that going to do? This is going to become a what? The x minus 5 is going to approach what value? X is, when we say x is approaching a value, we mean that the x is getting really close to that value. So as x approaches negative 2, it could be negative 1.99999 or negative 2.0001. We're just getting really close to it. We can't actually pick that value because it's forbidden. But in math, when we want to take a limit, we just want to see what happens when we get really close to it, right? So if I get really close to it, I'm going to get negative 4 times negative 7 over negative 7 times, what's that going to be? What's that approaching? As x approaches negative 2, isn't that approaching a value of 0? That's forbidden, right? But it's going to be it's not actually 0, it's going to be just a number that's getting close to 0. It's a really small number, right? So it's actually not 0. It's just a number very close to 0. What's infinitely close to 0? Now think what the behavior of the function is going to be there. I'm going to get something like 28 on the top divided by what's negative 7 times a vanishingly small number? Basically 0, right? It's going to be a number that's very close to 0, right? So we end up with the overall behavior of this thing just being positive 28 divided by a really small number. What is 28 divided by a really small number? What's the size of that fraction? That's a really big number, isn't it? if I divide 28 by 0.00000001, I'm gonna get like an enormous number, right? That make sense? So what is the result of this then? What's going on as we get closer and closer and closer to -2, the value of the function is just gonna be exploding, right? And we don't know if it's gonna be a really big positive or negative number at this point. We'll deal with that in calculus, right? But we know that it's gonna be explosive, right? So that tells us then that at -2, we're getting what's called a vertical asymptote, right? The function is gonna be sectioned off, and it's going to, as the ant walks towards -2 from the left or from the right, he's gonna, we don't know which direction at this point, but he's gonna go flying up to infinity, positive or negative infinity, right? There's like a big wall in the function there that's gonna really change its behavior, okay? So we can add that. So we know that right here, is a vertical asymptote. So we'll add that to our picture. Okay, there it is. That tells us a lot. That tells us a lot, because we know that the function, like, let's just say, we'll figure out in a little bit, is the function above or below the x-axis here? If it's above, we know it's going to do something like that. Tells us a lot about the behavior of the function, okay? Now let's look at this other place. At this other place that we couldn't go, which is 5, right? F of x, algebraically, if we look at f of x, those two factors would cancel, wouldn't they? Right? If I cancel those, I would end up with a simpler function. It would just be -4 over, if those cancel, x plus 2, right? Okay, let's look at our function real quick. Let's just graph this thing. I want you to see something.
Did you select it and then like backspace so that it highlighted it? What did you press?
I just hit shift and highlight it, yeah. Okay, so here's our function. Okay, what do you know? Notice we've got a vertical asymptote at -2, right? We were right on that, okay? If I test the value of this function at 5, what do you think I'm going to get? Undefined. Okay, so what that means is, if we were going to be accurate with our graph here, Desmos doesn't do this, but there's one little point. If I were to trace along this thing, it's defined everywhere on the, not at the vertical asymptote obviously, but every place else on the graph it's defined, except at x equals 5, there's what we call a hole in the function. There's one point that's missing. All the points around it are defined, but at 5, the function's undefined. If I put in a value very close to 5, like if I put in 5.00001, that's fine. It gives me back a value, right? But as soon as I try to put in the value 5, it knows that the function's undefined. So the way we represent that graphically, when we graph a function, we'd have to do something like this. At 5, we'd have to put a little open circle there telling us that there is, at that one point, there's a hole. That's missing, right? How big is that hole? Infinitely small, right? Could you fall through it? No, you couldn't, because it's infinitely small. But it's there, right? The ants we're dealing with, by the way, are point-like in size, so they could fall through.
You don't know how skinny I am.
Okay, now notice that's a lot different, though. That's a lot different than the asymptote. Isn't that weird? Right? This is really kind of a big deal. We got these two places where the function doesn't exist. One of them is this almost unnoticeable little hole. The other one is this massive vertical asymptote that changes everything, right? What's the difference? Can you tell me what's different about, how come one of those is a vertical asymptote and one of them is just a wimpy little hole? -2 is the vertical asymptote. That's the zero that's a negative, or that's a vertical asymptote, and 5 is the zero that's a hole. Okay, I'll give you, what do you think?
When you plug the 5 in, what you do,
Yeah, okay, yeah, it's different. It's different. Now look what happened when we canceled the x minus 5 factors. We created this other function that looks a lot simpler. Let's call it g of x, and let's look at the graph of that one. So if we graph g of x, equals, what was it, -4 over x plus 2, right? It's the same thing. Look at that. It totally, if I turn g of x off, look what happens. It exactly overlaps. I guess I got to move him over, don't I? It exactly overlaps with the red function, doesn't it? Is it exactly the same? Is there any point that's different on g of x than on f of x? Ah, 5. Okay, let's check 5. Oh, g of 5 exists. It's fine. G of 5 is there, right? So what did we do? This is pretty interesting. When we algebraically canceled out the x minus 5s, we changed the function. We filled in the hole. That's what we did, right? But it's a different function. It's not the same function. We have to call it something like g of x instead of f of x, right? Okay, so what we find then is that if we have a unique zero of the denominator, meaning a zero of the denominator that is not also a zero of the numerator, like -2. -2 is a zero of the bottom but not the top. That has to correspond to a vertical asymptote. If I have a shared zero of the top and the bottom, like 5, that corresponds to a hole in the function. Okay? Make sense? So in our graph, we can recognize that right away. Now that we know the trick, we could have seen, just when this was in factored form, we know that these are both undefined, but we could have done something like, okay, at -2, I can see that that's a unique zero of the bottom, and so that becomes a vertical asymptote. So we'll put a VA above the -2. And that tells us we know we're getting a dramatic vertical asymptote. Now over here, this one, the 5 was a shared zero, so that's just an innocuous little hole in the function, right? And that tells us a lot. Okay, so now we can go down here to our graph, and we're going to do the same kind of thing we did before. Now we have no x-intercepts this time, right? There's no place where the function actually touches the x-intercept, or touches the x-axis, okay? But we had these other places. We had an undefined function at -2, and we had a hole at 5, right? So all we got to do now is we just have to figure out, we're going to play our little trick with the factors, and we just want to figure out, well, what's the sign of the function going to be around those places, and that's going to dictate what the function does, okay? So we're going to go up here, and we're going to have to pick these test points again. So we'll pick one to the left of the vertical asymptote, so let's just pick one out here at like -10. We could pick one at 0 in between, that's a convenient one. And then up here we could pick one at like 10. Okay, and we're just going to play the same game we did before. We'll go up to our factored version of the function, and we'll just figure out what the overall sign's going to be. So if I plug in -10, I'm going to need to erase some stuff here. Just erase all this. Okay, so what do we get? What is f of -10? I'm going to get, on the top, I get -4, which is always negative, times negative, right? Divided by negative times negative. So then we got to figure out what's the overall sign at the top. Positive, and the bottom. Positive divided by positive is always positive, okay? So we got a positive function there, okay? So that tells us already, we kind of know what's going on then. We know that the function's doing this. Right? That's the behavior, okay? How about at 0? At 0, I'm going to get negative times negative over negative times positive, no, at 0, positive, which gives us positive over negative, so the overall sign is negative. Okay, how about at 10? Space again. Yeah. What's that? Let's see if we can just figure out what the overall sign of the top is going to be at 10. I'm going to get negative times positive, which is negative, divided by positive times positive, so it's negative. Okay, that's everything we need to know, right? We know that the function's going to be below the x-axis over here the whole time. If we want to know where the hole actually is, well, what would we do? Well, we could plug it into, when we cancel the 5's out, this is a good trick. And this is, once again, this is kind of like a deeper calculus concept. But this is how we, if we tried to take this limit as x approached 0, or x approached 5, we would have gotten an answer of 0 over 0, right? Well, 0 over 5 we understand. That equals 0, right? 5 over 0 we sort of understand, because that's a vertical asymptote. But what the heck is 0 over 0? That's actually what we call an indeterminate form in calculus. It means we have to do some more work to figure it out. And the more work that we would do is we would cancel those factors and create a new function that fills in the hole and just see what the value of that function is at 5. If I plug 5 in there, I get negative 4 over 7. And so, I mean, this is way above. I'm not going to ever test you on this year, but just so you can kind of get an idea of what we're doing in future years. At 5, the hole that we're filling in would be at the point 5, what did we say it was, negative 4/7. So if you want to get a really accurate estimate of where that hole is, that's where it would be. Do we care about that this year? No, we don't. But we can do the function, right? We know that it's negative the whole time, so it has to be doing that. Okay? And we do know, but we do have to add that there is a hole at 5. That's our graph of our function. Yep.
So isn't 0 also horizontal?
It is. We get a horizontal asymptote because of this right here. Okay, that's important. Because our limit as x approaches plus or minus infinity is 0, our horizontal asymptote is the line y equals 0. Okay, and we want to kind of put that on our, when we compile all our data here, we want to write the equation of the horizontal asymptote, but really we get it right here. Okay. The limit as x approaches negative infinity is 0. The limit of the function as x approaches infinity is y equals 0. So that's telling us that we've got a horizontal asymptote at y equals 0. Okay? So there's the equation of our horizontal asymptote. What's the equation of our vertical asymptote? X equals negative 2. Right? Okay, get the idea? Okay, it's a lot of stuff. But it's pretty amazing what we're able to do then. I mean, we can get an accurate sketch of that graph. It's a pretty crazy looking graph just by knowing, where the asymptotes are. The asymptotes, when you get to the next level, kind of when we do a lot of this in calculus, you kind of think about the asymptotes as being the skeleton of the function. You can define the asymptotes, then you pretty much have an idea what the function has to do. You can fill in all the particulars by doing calculus. All right, we're out here at 25. Okay, we'll look at one or two more of these tomorrow. I got a couple little tweaks on the assignment, so that probably won't be available until tomorrow anyway.
Oh my God. I got mice in there.